4, you're often not going to get a lot of mean value theorem questions, and most of them are going to be of 1 or 2 varieties. So usually the variety of mean value theorem question that I typically think you're going to see is something like this. And I think I wrote this in someone's reflection. I'm going to use it again because it's not a terrible, I haven't checked the numbers. It might not be a beautiful example, but it's not a terrible example. So one type of mean value theorem question you could get asked to do is to find all values guaranteed by the mean value theorem for the function f of x equal to x cubed minus 6x squared. It's kind of my go-to cubic function. It's a nice one. It's got some nice qualities. On the interval from -1 to 7. Okay, so let me draw it, and we'll talk about what this means. So this function looks approximately like this. It's got an x-intercept at 6 and at 0, and we're going from -1 to +7. So here's the point, 7 comma whatever, it's 749 in case you're curious. Here's the point, -1, -7. And I know those points because I've looked at this function a lot. So the idea is that for this function, there should be, because of the mean, so I should back up a little bit. The function is definitely continuous and differentiable everywhere. It is a polynomial. Polynomials are nice everywhere all the time. We love polynomials. They love us. We're all friends. The mean value theorem says that there is at least one value between -1 and 7. There could be more, but there's at least one, since the function is continuous and differentiable, where the slope of the tangent line is equal to the slope of the line that connects that point to that point, or the endpoints. So there is at least one point on this curve between here and here where the slope of the tangent line is the same as the slope of that line, where the tangent line is parallel to that line. And it looks like there's probably one maybe here-ish. And there might also be one like right about here. So it looks like in this case, we're going to get 2. But that's the whole idea. Is so putting a finer point on it, we're looking for all the solutions to, I should say solutions between -1 and 7 to the equation f prime of x. So people write f prime of c, doesn't matter, either way, equals f of 7 minus f of -1 over 7 minus -1. Right? You're finding the slope between these 2 points. That's the difference in the y's over the difference in the x's. And you're saying it's got to equal the derivative of this somewhere. Okay. And depending on the equation, sometimes this is really not terrible. Sometimes it is literally impossible to solve. We know there's a solution because the mean value theorem guarantees one, but the algebra is sometimes quite actually not possible to find the solution to. That's okay. Although I should say, if they ask us to actually find them, right, if the question says find them, it should be solvable. If it says show there is a value, you just have to cite the mean value theorem. All right, so let's take a look here. So I'm going to factor this to make life a little bit easier. So my f of x here is x squared times x minus 6. I can see that f of 7 is 49 times 1, which is 49. And f of -1 is 1 times -1 minus 6, which is -7. Right there, -7. So I'm trying to solve f prime of x, which I'll do in a minute, equal to f of 7, which is 49, minus -7 over 7 plus 1. And my derivative here, my f prime of x, is 3x squared minus 12x. So let's see, I'm trying to solve 3x squared minus 12x equal to, let's see, 49 plus 7 is 56. 56 divided by 8 is 7. So I'm trying to solve 3x squared minus 12x equals 7. And that's definitely something we can solve. It's a quadratic. I'm going to erase this picture now, unless anyone, does anyone want me to say anything else about this picture before I erase it? Going once, going twice. Erased. I can always go out again if there's no pictures about it. So that reminds me of the time when I bought a bike at the bike auction from the UC Davis Police Department. It's a long time ago. But they used to like auction bikes. So they probably still do, I mean, like in normal times. Anyway, not important at all. Let's go ahead and solve this. So once you get to this point, it shouldn't be hard, right? We're trying to solve 3x squared minus 12x minus 7 equal to 0. And although this could factor, it's possible. It probably doesn't. I don't want to waste my time trying to see if it factors not. I'm just going to go straight to the quadratic formula. So my solutions, my possible solutions are x equal to negative b plus or minus the square root of negative 12 squared, so 144, minus 4 times 3 times negative 7, all over 2 times 3. So it's going to simplify to 12 plus or minus, let's see, all right, 7 times 3 is 21, times 4 is 84, and it is a positive 84 because the negative comes to negative. So we've got 144 plus 84, which is 228. Yeah. Which is definitely not a square number. All over 6. It's pretty close to a square number, though. It's really close to 225, which is 15 squared. So here's what I'm seeing. I've got close to 12 plus or minus 15 all over 6, which would be approximately 27 over 6, which is like 4 point something. It's actually 4.5. And negative 3 over 6, which both of those, even though they're not my exact numbers, both of those are certainly in the interval. So I know that both these numbers, and maybe you could simplify this a little bit. I don't want to simplify it. It looks terrible. I'm going to leave it like this, even though I could almost definitely simplify that part. We need to. So we know that both of those numbers, 12 plus root 228 over 6 and 12 minus root 228 over 6, those are both values of x that are indeed guaranteed by the mean value theorem. Okay. Let me check something real quick. I don't remember, and you guys, I feel like I did. Yeah. So I did. Yeah, I definitely did do one of the questions before where we talked about how. So the other type of question is show that. This is where I was actually going to go grab an example real quick. I don't know if I need to do this question, but I should mention it. Let's look at that one. That's not what I wanted. Go back. Sorry, one sec. Yeah. So I want to show that this function, f of x equal to x to the 5th plus 2x squared minus 2 has exactly 1, 0, or 1 root. We did a question like this before, where I talked about how it was an existence and uniqueness proof, where you first had to show that there is a solution, usually by using the intermediate value theorem. And then you had to show that there's only one solution by showing that there couldn't be 2. I can do this one, but we did do one like that before. So what I'm trying to say is these are the 2 flavors of questions that you usually get asked about the mean value theorem. Flavor 1, the more typical flavor, find the solution, find the values guaranteed by the mean value theorem. Flavor 2, less typical, usually not a test question, sometimes a homework question, although really this is a homework question where you actually had I couldn't imagine how you would ask this question on web work. It seems like it would be hard to kind of do, although I don't know, it's possible, I'm sure. Let's outline how to do this problem real quick. I'm going to be light on the detail, not light on the specifics here. So part one, existence. So we show it exists by the intermediate value theorem. We say, okay, well, I don't know what the actual solution to that is, but I know that it's certainly continuous and differentiable, right? I mean, polynomial, good times. We know that f of 0 is 0 plus 0 minus 2, and f of 1 is 1 plus 2 minus 2. So between 0 and 1, the function goes from negative 2 to positive 1, so it has to cross 0 somewhere. So by the intermediate value theorem, there is a number that lives between 0 and 1. Such that, let's call it C, f of C is indeed equal to 0. So we just showed, we don't know what it is, but we showed that there is definitely a solution to this equation equal to 0, or to finding a root of this equation. And that root of the equation is between 0 and 1. The second part is always kind of wonky. Uniqueness. So that there can be only one solution. Okay, so the way to show there's only one of a thing in math is to say, well, I think there's two. And then show that that can't really be true. So there's two. Assume there are two zeros. Or two roots, whatever you want to call them. Let's call them A and B, which is fairly standard. And then here's the thing. If A and B are both roots, then we know that f of A is equal to f of B is equal to 0 in this particular case. And then Rolle's theorem, or the mean value theorem, really, again, Rolle's theorem is just this particular case, the mean value theorem, where f of A and f of B are equal to each other. They don't have to be equal to 0, but they do have to be equal to each other to be Rolle's theorem. But I'm just going to say the mean value theorem. So by the mean value theorem, between A and B, there is a number between A and B where the derivative is equal to the slope between the endpoints, where f prime of x, or f prime of, let's call it f prime of the number, is equal to f of b minus f of a, all over b minus a. But we know that's 0. Because f of b minus f of a is 0, and b minus a is not 0. B minus a, b and a aren't the same. There are two distinct roots. Okay, and this is where we're about to get a contradiction. And yeah, I'm not out of room here. I can just jump here. So check it out. If I try and actually solve this, well, my derivative is 5x to the 4th. Did I make up a dumb example? Did I write something wrong? And I'm like, shoot, did I screw up? Yeah, I did screw up. Sorry, I screwed up still, but it's okay. I can fix it. This is supposed to be x cubed, not x squared. Fortunately, that doesn't change anything we've done so far. Sorry about that. Let me talk through my thought process here about how I know I was making a mistake right there. So first of all, let me just go back and say f of 0 is still negative 2, f of 1 is still positive 1. Intermediate value theorem still holds. The uniqueness part argument is still the same, right? We're assuming there's an A and B where f of A and f of B are both 0. Now we're saying there has to be a number where the derivative is equal to 0. And now that I've got the right function up here, my derivative is 5x to the 4th plus 6x squared. And why is this, like, am I making all the mistakes here? I'm like, why is this example dumb? Oh, I think I know what's happening here. Yeah. This example is a little bit tricky. Okay, that's fine. Sure. So is this equal to 0? Well, it actually is. Right there. Sorry, so this example is a little bit different than the ones I've done before. That's okay. We're still going to be fine. So where is this equal to 0? I can factor out x squared. It's equal to 0 when x is equal to 0. That's interesting. So what's going on here? Well, let me ask you a question. Can our derivative be 0? Sorry, I'm saying something a little bit wrong here. And that's all right. I just need to back up for 1 sec. Sorry, let me just back up for 1 second. So I don't say something extra stupid here. One moment. Yeah, okay, that's what I thought, but I just wanted to make sure. So here's the thing. Sorry, I need to make sure I say this very, very specifically. Yeah, okay, cool. So the thing I was not saying here that I missed, that's all right. I'm like, it's okay, I made a mistake. No. So the thing is that we've used these values here, 0 and 1, to find a place where it's negative and a place where it's positive. And so what has to be true is that these two values that we're assuming are there, well, yeah. Since we're really kind of using the interval from 0 to 1. I feel like this, sorry, I apologize. I have to make sure that this is right because I feel like now that I'm looking at this, it feels kind of wonky. Yeah. Okay. Okay, cool. So let me back it up just a little bit. So we know that there is definitely a solution between 0 and 1. And it's definitely not at 0 because f of 0 is negative 2. So the thing and I apologize because I was maybe a little overconfident when I started this example. So the fact that our solution is between 0 and 1 means it's not 0 and not 1. Right? It's definitely not 0, it's definitely not 1. So then by the mean value theorem, aka Rolle's theorem in this particular case, we know there has to be a place between 0 and 1 where the derivative is equal to 0. But the only place where the derivative is 0 is 0. And that's not actually in between, right? It can't actually be the endpoint. So because the only solution is actually not in the open interval from 0 to 1, right? This is kind of a very technical thing here, right? Where the solution to this actually has to be not at the endpoints. We can say, well, since the only solution we're finding actually is at an endpoint, we failed, right? We've contradicted the theorem. It says, well, the mean value theorem, the Rolle's theorem, says there has to be a number literally between the endpoints. Well, the endpoints are 0 and 1. Our answer is not between them. So then we can say that since our solution to this isn't where it's supposed to live, we have contradicted the theorem. And if we've contradicted the theorem, well, the theorem is actually true. So the assumption that we made to get us to this contradiction is what has to be not true. I'm sorry, I know that got maybe a little bit kind of weird at the end there. So there is not two solutions because that would contradict. That would lead to a contradiction in the theorem. Okay, so this is the other type of flavor that you sometimes get asked about the mean value theorem. Again, I don't think you're as likely to see this type of question in general. I do think you're moderately likely to see this type of question where someone says, find the values guaranteed by the mean value theorem. All right. Let me go back here one sec. Let's see, I had something else. Oh yeah. There was, so, sure, there's a couple ways I want to go here, which is generally true in this class. So someone asked me a question that I think is fairly easy to answer about having multiple absolute extrema. And I can think of two good examples of this. So first one is, let's look at, so I want to find all absolute extrema for f of x equal to, oh, what's that function I like to use sometimes? It's that one, I think. Yeah, it's that one. It's x to the fourth minus 4x squared. That should probably be all right. On the interval from, let's say, -3 to, oh, let's be careful. Yeah, -3 to 3. Now let's go -3 to 4. That's more interesting. Okay. So this is back to the types of questions where you're just finding the critical values. And you're trying to find absolute extrema, you're just plugging those critical values and the endpoints back into the original function to see if the map, which is the biggest and which is the smallest. So let's find our critical values, which I'm sure I've maybe, no, this is fine. So my derivative is 4x cubed minus 8x. I'm going to set that equal to 0. I'm going to factor out 4x. I'm up with an x squared minus 2. I might have picked different numbers. Oh well, this is fine. So my solutions are x equals 0 and plus or minus the square root of 2. Now we'll point out that all three of these critical values are in the interval. Root 2 is definitely less than 4. Negative root 2 is definitely bigger than -3. So everything is between -3 and 4. So then we're just going to evaluate this function at all of this. So I'm going to find f of 0, f of the square root of 2, f of negative square root of 2, and then also f of negative 3, and f of positive 4. And it might be easier if I factor the function as x squared times x squared minus 4. That seems like it might be easier. So let's plug in 0. If I plug in 0, I get 0. Let's use a different color. It'll be exciting. Christmas colors, green and red. All right. Let's plug in the square root of 2. And I think it is easier here. Square root of 2 squared is 2. Square root of 2 squared is 2. 2 times -2 is -4. And it's also the same for negative root 2. Negative root 2 squared is positive 2. Negative root 2 squared is positive 2. 2 times -2 is -4. F of -3, if I plug in -3, I'm going to get 9 times 5, which is 45. If I plug in positive 4, I'm going to get 16 times, 16 minus 4 is 12. 16 times 12 is, I don't know what that is. Let's see, it's, I think it's 192. Probably. Yeah, it is. Okay, so which of these is the biggest? Clearly 192. So we have an absolute max at x equal to 4 with a value of 192. For an absolute minimum, we have 2. We have an absolute minimum at square root of 2, and we also have an absolute minimum at negative square root of 2, because they both have the smallest y value. So it is possible for a function to have multiple absolute extrema, meaning it's possible for us to have multiple absolute maximums or multiple absolute minima, or both. Let me give you one more real easy example. An example all of you are very familiar with. We can look at the function cosine of x. Cosine of x has a lot of absolute extrema. And you can either pick an interval here or not. I'm not going to pick an interval. I'm just going to look at the function for a second and say, where's my cosine function? It starts here at 0, 1. And again at 2 pi, it has a y value of 1. And then pi has a value of 1. So it looks kind of like this. And it goes on and on and on. And it's got the point 0, 1, it's got the point 2 pi, comma 1, it's got the point 4 pi, comma 1. And you can certainly find the critical values by finding the derivative, which is negative sine, and setting it equal to 0 and getting 0 and pi, and sorry, 0 and 2 pi and pi. But, yeah. But I'm going to just say we have absolute maxima. We have an infinite number of absolute maxima at x equals 0, and at 2 pi, and at 4 pi, and at 6 pi, and really at negative 2 pi as well, and at negative 4 pi as well, at negative 2. This one has absolute maxima at every even multiple of pi. At 2 pi, at 4 pi, at 6 pi, etc., etc., etc. So a function can actually have a literal infinite number of absolute maximums, and also an infinite number of absolute minimums. Kind of neat. Not that important, but it is important to know that when you are asked to find where the absolute maxima or absolute minima are, there can in fact be more than one answer to that question. There can be multiple answers to that question. All right, and then I know I've kind of started down the graphing side of things, but let me answer a different question first that someone asked about, and then we will get back to talking about all the second derivative stuff that people have asked about. So someone asked a question about the derivative of an inverse question. This is specifically from Haas's class. Let me grab it here so I can see it. I'm going to change up the numbers a tiny bit just to make it less terrible. So let's say that our function was, what do I want to pick? What do I want to pick? That seems, so I'm trying to make something that's like not as awful as this, but also not terrible. Sure, let's say our function is 2x to the 5th. And this particular question asks us to do the following. It asks us to state whether the function is increasing or decreasing. So show that f of x is either always increasing or always decreasing, which your book, I think, yeah, your book definitely talks about this. Another way of saying this is that the function is monotonic. Right? The function is always increasing. It is monotonic. The function is always decreasing. It's called monotonic, meaning you have a singular direction. I'm probably butchering the tonic part. I'm sure tonic might not mean direction exactly, but close enough. It does one thing and one thing only. Either always increases or always decreases. So show that f of x is always increasing or always decreasing. And the way we're going to show that is by taking the derivative. The derivative here is, see, 10x to the 4th. And that derivative is certainly always greater than or equal to 0. And since the derivative is never negative, the function is always increasing. And in case you're curious, I should point out that yes, it is true that a function that is whose derivative is non-negative is always increasing as long as it's only 0 in a finite number of isolated points. Right? So it's okay that the derivative is 0 at 0 here. This function 2x to the 5th kind of looks like this. Wow, that's not the best job I've ever done drawing. But right, at 0, it kind of flattens out for a second, but it's increasing because as we move from left to right, the y values are always getting bigger. There's never a point that's further left that has a higher y value than a point that's further right. Okay. The second part of this is to then, I should actually back up to the point. The reason why we care about a function being monotonic is because any monotonic function is invertible, has an inverse, because it passes the horizontal line test. Right? This function here, I can draw a horizontal line and it will only pass through at most one point of the function. Right? And we need that to be true because when you find the inverse, you're flipping things around and the horizontal line becomes a vertical line and it has to pass the vertical line test to be a function. So that's why we care at launch. That's one of the reasons we care about a function being monotonic, is because it is then for sure invertible. So the second part of this asks us to find the derivative, that's not how you write that, the derivative of the inverse function in general. And I think there are two absolutely valid ways we could do this, and I will show you both of them. I will show you the way that I think makes sense, and then I'll show you the crazy thing I imagine that the book probably, or the author of this probably imagined when they thought about this question. So, to find the derivative of the inverse. So first of all, my function is 2x to the 5th. And I want to find the derivative of the inverse. Here's the first way. Find the inverse function. We know it's invertible. And then find the derivative of that. So to find the inverse function, switch x and y, solve for y. So switch y and x, solve for y. X over 2 is y to the 5th. So y equals x over 2 to the 1/5 power. And then take the derivative of that. So, whoops. Oh, come on. Sorry. So my inverse function is x over 2 to the 1/5 power. The derivative of that, which is always a pain to write. You write it like this, you write it like this. I'm just going to take the derivative. So I'm going to get 1/5 times x over 2 to the negative 4/5 power times the derivative of x over 2, which is 1/2. And at least for now, I'm not going to simplify that. If I was going to simplify, I would write it as 1/10 times x over 2 to the negative 4/5. Okay. The other way I imagine someone might want you to do this is by using the inverse derivative theorem. Or I think the book has a different name for that. I don't know if it actually has a specific name. Let me just look real quick here. It's on the page and it went away. No, it's in my textbook, it's in section 3.8, which I feel like isn't the case anymore. But they call it Theorem 3, the derivative rule for inverses. So, right, real catchy name, derivative rule for inverses. So here's the other way you could do it. You can say, you can find the derivative of f inverse by doing 1 over f prime of f inverse of x. And we have all the pieces for this. We have f inverse, it's literally right there. And I can find f prime. So can you. F prime of x is 10x to the 4th. So 1 over f prime of f inverse, instead of being 1 over 10x to the 4th, it's going to be 1 over 10 times my stuff to the 4th. But we know what f inverse is. It's, where'd you go? It's right there. It's right there. It's x over 2 to the 1/5 power. So you get 1 over 10 times x over 2 to the 1/5 to the 4th. But now look, these are the same. This is 1/10 times x over 2 to the negative 4/5, and I can write this as 1/10 times 1 over x over 2 to the 4/5 power, which is 1/10 times x over 2 to the negative 4/5. So either way you do it is right. I really, really don't know which way they want you to. I also do know it doesn't matter which way you do it, at least for this problem, because, and this is true always, whether you find the inverse and then take the derivative or use this weird inverse derivative theorem, the answer has to be the same. It might look a little different before you do any simplifying, but the answer has to be the same because you're finding the derivative of the thing either way. Derivatives don't change because you use a different method to find them. Yeah. I don't care. I just want to see the next question. I also noticed that question 18 on this assignment looked kind of similar. It was something to the effect of, sorry. I really like to make noises, I've noticed. So the next function is use the fact that increasing and decreasing functions are one-to-one, meaning that they have an inverse, to determine if the following function has an inverse. So here's the function. I'm going to make up something else. Let's say it's, I don't know, 2 minus 6x to the third power. Basically, if you have a function that is something to an odd power, it's always going to be monotonic. Odd powers are now, you can't have like a sum of odd powers. Like, for example, if your function was x to the fifth minus x cubed, even though both those powers are odd, you still have some like up and down. But that thing, for sure, without a doubt, is monotonic. One-to-one. Because its derivative is going to be always non-negative. Or maybe non-positive in this case. Right? The derivative is 3 times my stuff squared times the derivative of my stuff. And that ends up being negative 18 times 2 minus 6x quantity squared. That's always positive, or at least I should say that's always non-negative because it could be 0. But that's a negative. So a negative times a non-negative is a non-positive. So this thing is always less than or equal to 0, which means this function is always decreasing, which means that f of x is indeed one-to-one, or if you prefer, invertible. And these really do mean the same thing. Like they are always, if a function is always decreasing, that is equivalent to being invertible. And if a function is invertible, it has to always be decreasing or increasing. It has to be monotonic. You can't have one without the other. If you're monotonic, you have to be invertible. If you're invertible, you have to be monotonic. Yeah. Now, what if I had to find the derivative of the inverse here? Ugh. So here's the thing to know about finding the derivative of the inverse. Either way, you're going to have to find the inverse. Either you're going to find the inverse and then just take the derivative, or you're going to find the inverse and then plug it into the derivative, 1 over the derivative of the original thing. But either way, you have to start with, or you have to get to eventually, finding the inverse. So the inverse here, I've got y, sorry, I'm switching x and y. I've got x equal to 2 minus 6y to the third. Solve for y, so take the cube root. Equals 2 minus 6y, add 6y, subtract cube root. Let's write it as x to the 1/3. That seems like the smarter way to do it. Divide by 6. So the inverse function is 2 minus x to the 1/3 all over 6. Which, if I'm going to take the derivative, I'm probably going to write as, there's never enough room. I'm going to write as, I would probably write f inverse of x as 2 over 6, which is 1/3, minus 1/6 x to the negative 1/3. Because that's going to be way easier to differentiate or plug into than the way I've written it over there. And then you can either take the derivative of this, which I'm sure everyone is capable of doing. It's going to be positive 1/18 times x to the negative 4/3. It's kind of boring. Or we could do it the more exciting way. We could say that the derivative is 1 over f prime of f inverse. So we find f prime, which is, I feel like this is what they want, but this seems way more complicated. right? F prime is 3 times 2 minus 6x squared times -6, which I literally just noticed was right there. Sorry. I guess, okay, I can see the reason for doing it this way. If you've already done this work and you found the inverse, you could just really plug in your inverse. Okay, I think there's an argument for doing it this way. Oh, especially because things do, okay, this one does kind of come out nice. So if you do it this way, you get, and I'm going to go back to this because it actually might make, right, if I'm plugging this in for x here, things might actually turn out really nice. So look at what I get. I get 1 over the derivative, which is this, -18 times 2 minus 6 times my input squared. But then this is what's going in there. This 2 minus x to the 1/3 over 6. And look, things are going to cancel. 6's will cancel, 2's will cancel. So I could kind of see in this particular problem, okay, it does kind of come out nicely. I still think it's easier to do this, but here's how I get 1. Sorry, and I know I'm all over the place here because limited board space. I get this equal to -1 over 18. And then I've got 1 over 2 minus 6 times that. 2 minus x to the 1/3 over 6. And that quantity is getting squared. So look what happens. The 6's cancel. 2 minus x to the 1/3, the 2's cancel. And you just get -1/18 times 1 over positive x to the 1/3 squared. Which is definitely the same thing you would get if you, I did something dumb. You guys let me get rid of it. For some reason I wrote x to the -1/3 right there, but it shouldn't have been. It was still x to the positive 1/3. So then, yeah, the derivative of this is going to be -1/18 x to the -2/3, and the derivative of this is -1/18 times x to the -2/3. So those problems are kind of weird. Good thing I have a lid on my cup so I don't destroy my computer when I spill my water. Yeah, I did spill a little water, so let me just clean that up real quickly. That would be, I mean, I guess that would just destroy my keyboard, which, I mean, keyboards are replaceable. All right, enough of this weirdness. I mean, I'll say this theorem does kind of resurface if you get kind of deep into math. It's kind of there. I mean, it's always there. All right, let us move back towards, so let's talk about some second derivative stuff for a bit. And then depending on how much we want to do with that, we'll see. And after that, we will, yeah. So can you guys tell me, well, actually, no, let me do an example and then we'll bring it around. Yeah, okay, I'll do this. So there is this thing called the second derivative test for relative extrema. And instead of saying what the test is, I'm just going to show you, and then we'll come back and say what it is. And I'm going to give you like 3 separate examples, which are not too bad. So the first example, I'm going to go back to my favorite function because it's easy and it shows what I want, is the function x to the 3rd minus 6x squared. It's not my favorite, but it's my favorite for graphing stuff because it's not too hard. So I'm going to talk about how to find the relative extrema for this in 2 different ways. That's 4. In 2 different ways. In 2 different ways. The way we're going to do this is first the normal way, using the first derivative test. So first, either way, we have to find the critical values. Take my derivative, it's 3x squared minus 12x. Factor, 3x times x minus 4. And yes, we get the critical values, x equal to 0 and x equal to 4. And the way you would see if those were relative extrema using the first derivative test is the following. You draw the number line, you put your critical values on the number line, and then you ask, what's that first derivative doing? Well, pick a number larger than 4, like 7, and plug it in. That's positive, the whole thing's positive. And if you pick a number between 0 and 4, or you use the odd power to say the sign changes. But I'm going to pick 2. 3 times 2 is positive, 2 minus 4 is negative, so the whole thing is negative. And then pick something like -1, that's negative, the whole thing's positive. So knowing that the first derivative is positive, negative, positive, I can see that the actual function is increasing and then decreasing and then increasing. So using the first derivative test, I can see that I have a relative maximum at x equal to 0. Because the function went up and then went down. So it had to be a maximum right there at x equals 0. And I have a relative minimum at x equal to 4. Because the function went down and then it went up. So that's what we have. So that's how you can use the first derivative test to see if you have relative extrema. We can also use the second derivative test. So the second derivative test is the following. It says, all right, I'm going to take the second derivative. My second derivative here is, let's see, it is 6x minus 12. I don't care, but I will mention that the critical value for the second derivative is 2. If you plug in 2, the second derivative is equal to 0, which is a contender for being an inflection point. That's not what we're doing right now, though. What I do want to do is I want to evaluate the second derivative at each of these first derivative critical values. So what's f double prime of 0? Well, let's see. It's going to be 0 minus 12, which is negative 12. So here's what that tells me. This being a critical value of the first derivative means it could be a maximum, it could be a minimum, or it could be neither. But the second derivative being negative means it's concave down. And if you have a critical value where the first derivative is 0, and you know it's concave down there, it means it has to be a maximum, right? If my first derivative is 0, it means I'm flattening out. There's kind of only 3 options I'm flattening out. Either I'm flattening out like this, concave down. I'm flattening out like this, concave up, right? Remember when I say flattening out, I'm saying like horizontal tangent line, or I'm flattening out like this, which I know looks dumb, but where you have a, right, like, oh my God, James. Like right there is where it flattens out, and you have, right, it's increasing. So these are the 3 cases. You can either flatten out like this, concave down, relative maximum, flatten out like this, concave up, relative minimum, or flatten out like this, concave up over here, concave down here. I don't have a relative max or a relative min. So the point is that you can just take your critical values from the first derivative, plug them into the second derivative, and if it's negative, that means, that means we have a relative maximum because it's concave down. Or, I should say, and, if I plug in 4, f double prime of 4 is 24 minus 12, which is positive 12. And so since my second derivative is positive, concave up, I have a relative minimum, which totally agrees with what I said here already. The only downside to the second derivative test for relative extrema is that it's not always conclusive. Whereas the first derivative test will always tell you if you have a point that's a relative maximum, a point that's a relative minimum, or a point that's neither. Let me show you 2 more examples. And then we'll take a break. And then we'll, we'll after that. We'll do something. So, 2 examples about the, what's the word I'm looking for? About the, that's a word. about the inconclusiveness part. So let's look at the function x to the fourth. Oh, by the way, just so everyone can see it, right, the previous function looks like this. Right, here's our relative maximum at 0, 0. Here's our relative minimum at x equal to 4, y equal to f of 4. Right, this is f of x cubed minus 6x squared. And you can see, right, here at this relative minimum, it's concave up. Here at this relative maximum, it's concave down. So now let's look at kind of an ambiguous example. Let's say x to the fourth. The derivative is 4x cubed for sure. If I set that equal to 0, my critical value is indeed x equal to 0. And I can see from the first derivative test, well, clearly if I pick a number like 1, the first derivative is positive. If I pick a number like -1, the first derivative is negative. It's decreasing, increasing. Obviously, we have a relative minimum at x equals 0. Or if you want to say local, right? If you don't like the word relative, if I say relative, you should just hear the word local. I usually say relative. I don't know why. So we have a relative minimum at x equals 0. If you tried to use the second derivative test here, you wouldn't get very far. Well, that's not. I mean, you would do the work, right? You would find, okay, f double prime of x is 12x squared. And if we plug in 0, f double prime of 0 is 0. Meaning we don't actually have, it's not concave up or concave down at that particular point. So if we had not done this part here, we wouldn't know if it was a relative max or relative min or neither. On the other hand, and just to kind of, so I want to really emphasize this point. This graph, I'm never good at graphing this graph, but this graph kind of looks like a parabola, except it's more extreme. It's extreme. It kind of does this. It's like, I made it like too parabola-y. It really kind of does more like wobble, 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 wobble. It's kind of like wobble. It gets very flat looking at the bottom there. And that's true for higher even powers as well. So it's like x to the 6 or x to the 8. And so you might like think, James, that kind of looks pretty concave up. And I would agree that at any other point besides 0, it is concave up. Right? If you plug in 1, the second derivative is positive. If you plug in -1, but any other point, it's concave. But at 0, the second derivative is 0. So the concavity is kind of wonky. And let me show you my last example now, which is, let's say g of x is x to the fourth minus 4x cubed. So here's what this function looks like. So the first derivative, I'm going to skip the first derivative test on this one at first, is 4x cubed minus 12x squared. I'm going to set that equal to 0 to find the critical values. Factor out of 4x squared up to the x minus 3. So my critical values are x equal to 0 and x equal to 3. I'm going to jump straight to the second derivative. I guess I need the root here, sorry. So my second derivative here is going to be, let's see, 12x squared minus 24x. And I'm going to factor out the 12x times x minus 2. If I plug in 3, I get 36 times 1, which is positive. Means it's concave up, which means it's a relative minimum. So we have a relative minimum at x equal to 3. On the other hand, if I plug in 0, g double prime of 0 is 0. Meaning it could be like this one, where I have a relative minimum there. But it could be something else, right? So if your second derivative is 0, we don't know. Could be relative min, could be relative max, could be neither. Because neither is probably an inflection point, by the way. So if we go back to the first derivative test, we can see that if you plug in a number like 4, positive, positive, plug in a number like 2, positive, negative, plug in a number like -1, positive, negative. So it's decreasing, decreasing, increasing. So clearly at 3, we do have a relative minimum like we already knew we did. And at 0, it's decreasing, decreasing, meaning we don't have a relative max or a relative min here. We have a neither. It's neither a max nor a min at this critical value. So I really want to stress here, when the second derivative was 0, we got a relative minimum. Here, when the second derivative was 0, we got neither a min nor a max. So if the second derivative is 0, you can't use that to say anything about if your critical value from the first derivative was a max or a min or a neither. Yeah, so that's what the second derivative test for relative extrema is. It says basically it says the following. If you have a critical value for the first derivative, so if f prime of c is equal to 0, and either, and 1, f double prime of c is negative, then we have a max at x equals c. If f double prime of c is positive, we have a minimum at x equals c. And if the second derivative at my first derivative critical value is 0, then we don't know. Then you need to go back and do the first derivative test. What I want to stress about this is, one, I don't do this. I mean, like, I would do it if someone told me to do it. But I don't like this because, first of all, if I'm graphing, usually I'm looking at the first derivative anyway, and I'm looking at the sign chart for it. So this seems really superfluous. Second of all, I also don't like it because sometimes you don't get an answer. So I wouldn't use the second derivative test for first derivative critical values unless you have to, because someone has told you, I want you to do it this way. The other thing I will mention about this, and then we'll take a 6-minute break, is that it's slightly counterintuitive at first, because when your second derivative is negative, you get a maximum, and often we're like, oh, negative means minimum. That's not the case here, right? Second derivative being negative meaning second derivative negative meaning you're concave down, so you have a maximum. Second derivative being positive means concave up, so you have a minimum at the bottom of the bowl of concavity. I want to point out, before we move on to talking about some optimization problems, that for that previous function, f of x equal to x to the fourth minus 4x cubed, that we definitely, like we were saying before, we have a relative minimum at 3, and we have a not min or not maximum 0. And 0 and 3 are both critical values for the first derivative. For the second derivative, which is 12x squared minus 24x, we factored out 12x and got 12x times x minus 2. The second derivative critical values are also 0, and x equal to 2. And so those values are where the concavity might change. So just like the first derivative critical values are where the function might change from increasing to decreasing or decreasing to increasing, because the first derivative might change signs. The second derivative critical values are where the second derivative might change signs. So that's where you might change from positive concavity to negative or vice versa. So if we want to take a look real quick, we can see that if we have a number that's larger than 2 and we plug it into the second derivative, we get a positive number times a positive number. We have a number between 0 and 2, like 1, we have positive times a negative. A number less than 0, like -1, we have a negative times a negative. So this function is indeed concave up, concave down, concave up. So if you're asked about the intervals of concavity, you could say it's concave up on the interval from -infinity to 0, union 2 to infinity. You could say it's concave down on the interval from 0 to 2. And then we would also say that we have inflection points at both 0 and 2, because at both of those places, the concavity has changed from positive to negative, and or negative to positive, and the function is defined there. Right? You can't change concavity. You can't have an inflection point at a place where the function is undefined. So here we would say there are inflection points at x equals 0 and x equals 2. Or if you want to be more specific, you have an inflection point at 0, 0, right? So you plug in 0, you get 0. You have an inflection point at 2, comma, f of 2, which is 16 minus 32, which is negative 16. So those would be the inflection points for this particular function where the concavity changes. Just to contrast that, if my function was, say, I'm going to make it real easy. Real easy? Real easy. If my function was 4 over x minus 3, and although I could use the quotient rule, I'm not. I'm going to write it as 4 times x minus 3 to the negative first. We can clearly see we have a vertical asymptote at 3. I'm going to graph this function before I do anything else. Vertical asymptote at 3. And I have a y-intercept at negative 4/3. I have a horizontal asymptote at 0 because the degree on top is less than the degree on the bottom. So it looks like this. And although we haven't verified it yet, it certainly looks like it's concave down over here and concave up over here. It is. Now, I think you also can all see we don't have an inflection point where the concavity changes from concave down to concave up because the function is undefined there. You have a vertical asymptote. So you can't have an inflection point where you have a vertical asymptote. You can't have a relative of extrema where you have a vertical asymptote. Let's find the things. So here, my first derivative, I'm just going to bring that down. It's going to be negative 4 times x minus 3 to the negative second times positive 1, which I could rewrite as negative 4 over x minus 3 squared. I would say we have a critical value at 3. A book would say we do not have a critical value at 3. We have a value that's important to include on the first derivative number line. So really, 3 makes the first derivative undefined. And even though it's not really a critical value, because to be a critical value, the original function has to be defined there, it's still a place where the sign of the derivative might change. And so if I'm doing the first derivative number line, I'm going to include 3, and only 3, because it's my only place where the derivative is undefined. Over here on the right, if I plug in a number like 4, negative, positive. Over on the left, if I plug in a number like 2, negative, positive. So it's decreasing, decreasing. Just like my graph shows. Decreasing, decreasing. So I'd say it's decreasing on the interval from negative infinity to 3, union 3 to infinity. We have to break it up at 3 because the function's undefined at 3. You can't include 3 in the interval of decreasing because nothing's happening at 3. It's undefined at 3. You can't be decreasing there. And then for the second derivative, I'm going to take the derivative of this, written this way. I'm going to get an 8 times x minus 3 to the negative third, which is 8 over x minus 3 cubed. Again, 3 is the only value where this thing might change signs. So I'm including that on my second derivative sign chart. And I see that if I'm bigger than 3, like 4, this thing's positive. If I'm smaller than 3, like 2, this thing's negative. So it's concave down and then concave up. So it's concave down from negative infinity to 3, like my picture shows. It's concave up from 3 to infinity. But we don't have an inflection point where the concavity changes because the function is undefined there. One thing I just started doing when I'm graphing things, I literally just today was like, this is a good idea. Why have I never done this before? Is if you know that a function is undefined at a point, and it's an important point. I mean, usually, if you've got a vertical asymptote, it's always going to be showing up as a place where the first and second and further derivatives are undefined. I think it's not a bad idea to draw an open circle around that point to remind yourself, oh, that point's not included in my interval. It is junk. I kind of like this. I think it's a decent idea that I came up with today. Kudos to me. I'm not just kidding. Sometimes I have good ideas. Sometimes I don't. All right, so that's most of what there is to the second derivative, right? We see where it's positive, that's where it's concave up. We see where it's negative, that's where the function is concave down. Yeah, all right. So let's talk about some optimization problems. Let's start with this one. That clearly, when this was done last time, was closer to Halloween. So here's what we're going to say. We want to construct a box, construct an open top box, meaning three-dimensional, right? Like a box you put stuff in, with a square base so typically the way this next part is phrased is using so much square inches of material. What they mean by that is they want the surface area to be a certain amount. So that uses 108 square inches of material. This is just a tricky way of saying that we want the surface area to be 108 square inches. So if someone says you have 108 inches of 108 square inches of material, that means they want your surface area to be that much. And I will also point out, I'll tell you later. So, and holds the greatest amount of volume. Maybe I should say design, because we're not going to construct it, we're going to design it. So what I really mean by this is, tell me the dimensions of the box, right? Tell me the dimensions that maximize the amount of volume it will hold. So we could, right, I mean, there are lots of boxes you could make that have 108 square inches of material. I could have, say, this box, this tall, skinny box, where the square base was 2 inches by 2 inches, and the height was 13 inches. So they can use the symbol for inches, which is a little, and that definitely, actually I think that would have 108 square inches of surface area. Let's see. The bottom is going to be 4 square inches, plus each face is going to be 26 square inches. So 4 times 26, that's going to be, let's see, 52, 104 plus 4, that's 108. With 100, my zero, that looks like garbage. So this box, using 108 square inches of material, would have a volume of 2 times 2 times 13, which is 4 times 13, which is 52 cubic inches. Whereas a different shape, maybe, I was going to come up with something a little bit different. Sorry, now I'm like trying to think of a better shape here. Yeah, it's hard to come up with perfect shapes. Here's the example that I have going for me. Yeah. So here's, whoops, oh boy, come on, you can draw this picture. So here's my box that really looks more like a tray. Right, it's an open top box. I'm just putting all my, this was supposed to be a Halloween box with my candy in. So here, okay, 2 inches by 2 inches, that's kind of, not gonna be able to fit candy in that box real well. This box, well, it's wider, and it's about approximately 8.5 inches by 8.5 inches by 1 inch high. Again, the surface area here is 8.5 squared plus 8.5 plus 8.5 plus 8.5 plus 4 times 8.5. It's not exactly 8.5, but it's close enough. 8.5 squared is about, let's see, 8.5 squared is 72.25. And 4 times 8.5 is 34. So I'm sure these are both supposed to be a little bit bigger. So this is really supposed to be like 73 plus 35. Yeah, let's just say it. Let's use an approximate there. The point being that this box, which is still using about the same amount of surface area, about the same amount of material, holds a vastly different volume. Like the volume here is 8.5 squared times 1, which is going to be approximately that 73 number. 52 cubic inches, 73 cubic inches. So I want to find the box that holds the most volume. All right, so this is the kind of essence of an optimization problem. You're given some constraint and you were asked to maximize or minimize some other thing. And this is one of the reasons we've been talking about finding maxima and minima of functions, so that we can set up a function that represents the volume of the box and then take its derivative to find the critical values to see where you might have a maximum volume. So let's do the thing. So here is my general box. And all I know about this box, well, I know a couple things. I know that the base should be square, meaning this length and this length should be the same. I don't actually know what those lengths are, so I'm going to give them variable names. And then this height here doesn't have to be the same, so I should give it a different variable name. It's called y. And I know this surface, actually, so I usually start off my process by first drawing a picture. And then the first thing I do is I write down the thing I want to maximize. I want to maximize the volume. So I find an equation for volume. For an open top box, it's pretty straightforward. It's just x times y, or base times depth times height. So the volume here is x squared times y. And I want to maximize this. So how do we usually maximize a thing? We take its derivative, and then we set that equal to 0 to find the critical values. The problem, this will almost always be true, is that the thing we're trying to maximize here is a function of too many variables, or 2 variables. Usually it's 2, sometimes it's 3. But typically we want it to be a function of 1 variable so that we can differentiate it and then set that derivative equal to 0 and solve for the one thing. So we often have to then say, well, there should be some constraint. There should be some way of relating the variables we are interested in. In this case, our constraint is that our surface area has to equal 108 inches. That should be very clear because this comes up a lot. The thing you want to maximize is never equal to a particular number until the very end when you've actually found the volume. So you're always starting off with something you want to maximize. It's volume equal to equation, not equal to a number. The constraint, on the other hand, the limiting piece of information is something, some known quantity about the shape equal to a number, right? We only have 108 square inches of material to work with that we're allowed to have our box used for some obscure reason. So I need to find the equation for the surface area of this shape. Well, this box, if I'm a little more explicit with my picture here, the dimensions of this box are x by x by y. The bottom has an area of x squared. And each face of the box, that's xy, that's xy, that's xy, that's xy. So I have 4 xy's. And there is no top, but if there was a top, there would be another x squared, so it would be 2x squared. So my surface area needs to be 108 square inches. So now, this is where we typically solve for one of our variables. So step 3, isolate one of the variables in the constraint. And typically you want to choose the thing that is just easier. That's almost always the case. What's easier to solve for here? Is it easier to isolate x or is it easier to isolate y? I should have got more water when I had a break. Oh well, I'll make it the next 22 minutes. Yeah, exactly, right? There's only one y here. Isolating x would be actually very hard. We'd have to like complete the square, which would feel dumb. No, we should definitely solve for y. So 4xy equals 108 minus x squared, and then divide by 4x to get that y equals 108 minus x squared over 4x. And you might break that up into two fractions and write it like as 108 over 4x, which reduces to 27 over x, and minus x squared over 4x, which reduces just x over 4. But before I start getting reducey, it's a word, right? Before I start reducing things, I would wait a minute. Because what we're going to do next is we're going to plug this in to the thing we're trying to maximize. So plug in to plug into the thing we want to maximize. Or I should say thing we want to optimize. So I'm trying to optimize volume, so I'm going to plug in that. So I'm going to get volume now as a function of just the variable x. You don't have to write v of x, but I like to. Is going to be x squared times 108 minus x squared over 4x. You'll notice our lives are a little easier. We can cancel an x here and an x there. So I could really write this as volume equals, I'd probably factor out the 1/4 and write it as 1/4 times x times 108 minus x squared. Or really, I'd probably distribute the x and write it as volume equals 1/4 times 108x minus x cubed. Because I know I want to take the derivative of this, and I'm trying to make my life as easy as possible by simplifying this in a way that's going to make it easy to differentiate. All right, I've run out of room, so let's go to the other side. So there's the thing I'm trying to maximize. And yeah, I can erase that. Let's keep the question up. So my volume as a function of x is 1/4 times 108x minus x cubed. It is not a bad idea at this point to think about the explicit domain for this function. So if you look at this as is, you'd be like, well, x could be anything, right? There's no domain restrictions if we look at this as it's written. But if we look back, there's a couple things that kind of have to be true. Well, first of all, it doesn't make sense for x to be negative, right? Or even really 0. Although you could make an argument. No, you couldn't really make an argument for x being 0 here. X kind of has to be bigger than 0, and x kind of has to be, well, because of this constraint here, x has to be less than the square root of 108. Because if x is the square root of 108, then x squared is 108, and this part can be 0, and that's using up all your surface area. Not really, it's kind of a lie. But the point is, often with these physical objects, you have some like actual real domain that you have to obey. So this kind of becomes important later on. What I'm going to say for right now is that it seems pretty clear that x, maybe not pretty clear, with a little bit of exploration, we kind of have to see that x has to be between these two numbers. It's not that important, but it is a little bit important. I should also make it clear that x actually really can't be 0, because if x were 0, y would be undefined in some bizarre way. Okay. Anyway, I'm kind of getting off the point. So let's take the derivative to find the critical values. So the derivative is 1/4 times 108 minus 3x squared. I can factor out a 3, and I get 3/4 times 108 divided by 3 is 36. And look, I get an answer. I actually get two answers, but one of them is garbage. My answers are, sorry, I set this equal to 0, right? I'm trying to find the critical values. My answers are plus or minus 6. But we know negative 6 would not make sense for the length of one of the sides of this box. So we get x equal to 6. Okay, let me ask you guys. Is this value of x going to maximize the volume? That's an excellent question. How do we know? Well, there's a couple ways we can check. You could either use the first derivative test, say, well, is it actually a maximum? So here's actually what I will say first of all. If someone's asking you to maximize a thing and you have found one critical value, it's going to be the maximum. Similarly, if someone's asking you to minimize a thing and you found one critical value, that value is going to give you the minimum. But I will point out in the real world, where math doesn't always do the thing you want it to do, it's not always the case. There's a story that someone told me when I was a math student, where an Air Force engineer was tasked with designing a plane, used a derivative to try to maximize the area that the wingspan was going to have. They took the derivative, set it equal to 0, found the critical value. It was like, great, maximum. They built the plane. I think it's not true, but it still makes a good story. They built the plane didn't fly because the guy didn't check to see that it was actually a minimum. He designed the plane with tiny little wings. I don't think it's really true. Although I do remember having a toy plane that was like, had really tiny wings, like one of those like little Matchbox kind of car plane things. Anyway, the point is you have to check to see if you actually have a max or actually have a min, because if you don't, you might actually have the wrong sort of thing. But in your class, it's going to be what the person is asking for. So here, if there's only one, if there's multiples, then you actually have to do some checking. So here, the way I'm going to check to see if it's a maximum, this is actually where it might make sense to use the second derivative test. So take the second derivative. The second derivative is going to be 3/4 times the derivative of this, which is just negative 2x. Plug in your critical point, and you can see that v double prime of 6 is going to be 3/4 times negative 12, which is negative. It's negative 9. I don't care really what it is. I care that it's negative, because if it's negative, that means it's concave down, which means we have a maximum. So this is a maximum. We have a maximum at x equal to 6. You could also use the first derivative test. We could say, hey, look, my derivative is 6. Here's my critical value, 6. And if I plug in a point that is bigger than 6, this is going to be negative. And I know if I plug in a point that's smaller than 6, but still bigger than 0, because you can't be too big, too small, right? It can't be negative values of x. So really, we don't want all of that. If I plug in a value that's less than 6, like 1, 36 minus 1 is positive. So it's increasing, decreasing, it's a maximum. And there's a theorem that says if you have one critical value on your interval, and it's increasing before and decreasing after, it's not just a relative maximum, it's an absolute maximum. Because there's nowhere else the function can be bigger, right? It was getting bigger, 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 bigger. It got the biggest, then it got smaller, 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 smaller. So if you have one critical value, the first derivative test will actually tell you that it's an absolute maximum or minimum. It's kind of cool. Now, the thing that people often miss, and I will say my question wasn't great, so it's easy to miss it here. Did we answer the question? Did we tell the person on the... So really, I probably should have phrased the question as, tell me the dimensions of the box that maximize the volume. And if we're asking that question, we haven't actually answered it yet. Because although we found what x is, the box has more than one dimension. The box has x and y. So we actually have to say what y is as well. Now, typically, to find the other dimension that you haven't found yet, there's almost always at this point an equation that has the thing you want. And it is right there. Typically, it's your isolated constraint solved for. So if I know that x is 6, I know that y is going to equal 108 minus 36 all over 24. 108 minus 36 is 72. 72 over 24 is 3. So the box that holds the most volume, that has 108 square inches of surface area, is a 6 inch by 6 inch by 3 inch high box. And it holds 6 times 6 times 3, which is 108. 108? That seems very coincidental. That is, so I will mention that that is a very big coincidence, right? We said we wanted the surface area to be 108. Okay, it is. It's really just a happenstance that the volume also is 108 square inches. This is not typically what happens. So don't be thinking like, oh, well, it's just the same thing, right? No, it's very much, I'm like, great. Coincidences are terrible when you're trying to show like something is just a general thing. So yeah, it's a coincidence here that that is what is happening. All right, let's look at another problem. I think, yeah, we got the problem with these problems is they're often long. But this is the whole kind of deal. You are going to set up an equation for the thing you want to optimize. Then you're going to find a constraint equation, isolate it, plug it back into the other one, derivative equal to 0, critical value, right? It's only like 12 steps. No, probably like 7 steps. And then see that that is giving you a max for min. All right, let's look at another example. I don't want that example or that example. I want none of those examples. Okay, so here's the example I want. It's similar but different. So I want to find the dimensions of the, I never remember what number is good here. We try to pick nice numbers often, but yeah. So find the dimensions of the cylindrical can that holds, how much volume do I want this thing to hold? Let's see. Sure, I'm going to say 125 pi cubic inches of volume that uses the least amount of material. Let me just think for a sec to make sure my number is actually what I want it to be. Oh no, I want, sorry. Yeah, I need to change that. Just one sec. I want that to be twice that amount. Apologies. I want it to be 250 pi. Okay, so I'm thinking like a can of beans. I want to find, right? I'm like, this isn't real world-esque in that I want to make a can that uses the least amount of metal possible that is going to hold the most amount of volume. Or specifically this amount of volume, which, yeah, I know it's a weird amount, but we want the pi to make our numerical lives easier. So I'm trying to find the dimensions of the cylindrical can that hold that much volume, that uses the least amount of material, AKA has the minimum surface area. So typically, often with three-dimensional shapes, you're given a volume and asked to minimize the amount of surface area, or you're given a surface area and asked to maximize the amount of volume. That is often the way these things work out. These are not the only things, but they're one of the things. All right. Picture time. So here's my can, and I'm trying to figure out what the radius and the height should be that are going to give me that much volume with the least amount of surface area. So I'm trying to minimize surface area. So I want to minimize the surface area. And the surface area of a cylinder is the top area plus the bottom area, which are both circles, plus the around part, which we talked about a class or two ago. That's going to be 2 pi RH. If you think about a paper towel going all the way around and you unroll it, it's a rectangle. The height is h. The length is the circumference, which is 2 pi r. So it's 2 pi r times h. All right. And I have a constraint. My constraint is that the volume, and the equation for volume is pi r squared h, right? The base area times the height. that volume has to equal 250 pi. Great. Now we're going to isolate a variable, and I would definitely pick h for two reasons. One is easier to solve for, right? I don't have to take a square root. Second, there's only one place I have to plug it in. So not only should you be thinking about which thing's easier to solve for here, you should also be thinking about, oh man, sorry, I'm hiccuping. You should also be thinking about which place you're going to have to plug that into, or how many places. And here, h is the clear winner for ease. I'm going to solve for h. H is going to equal 250 pi divided by pi r squared. Oh, that's convenient. So that's 250 over r squared. Let's plug it in right there. So my surface area is now equal to 2 pi r squared plus 2 pi rh over r, sorry, 2 pi r times 250 over r squared. We're going to differentiate that and set it equal to 0. But first, we're going to simplify it just a tiny bit. Let's go to the other side. We got enough time. So let's go back and see. I'm going to simplify this a little bit. I got 250, so I got 2 pi r squared. So surface area as a function of radius is 2 pi r squared. And here I can cancel an r. 250 times 2 pi is 500 pi over r, or 500 pi times r to the negative first, which is the way I want to write it if I'm going to have to take the derivative. Right? So instead of writing 500 pi over r, I don't want to really think about using the quotient rule. I'm going to say that's 500 pi times r to the negative first. Yes, you could factor out a 2 pi. I don't think we really need to. It's not going to make it any easier to do that. So let's take the derivative, which is step 12, right? That's like step 5. You don't have to number your steps. I just kind of like to value. So my derivative here is going to be 4 pi r minus 500 pi r to the negative second. And I'm going to set that equal to 0. Now, here is where I'm going to kind of break some of my own rules. Usually I would say you should solve an equation equal to 0 by factoring as much as possible. And you can totally do that here. You can factor out a 4 pi r to the negative second. But here it gets, you don't really have to do that. Instead, I'm going to do some rewriting. I'm going to say, well, this is 4 pi r minus 500 pi over r squared. And instead of factoring, I'm going to slide this over here and multiply both sides by r squared, which sometimes would be a problem. But I know since r isn't going to be 0, right, because 0 shouldn't be an answer for the radius of this can, it's safe to multiply both sides by r squared. So multiply both sides by r squared, I get 4 pi r cubed equals 500 pi. Dividing both sides by 4 pi, I get r cubed equal to 500 divided by 4 is 250 is 125. Sorry, divided by 2 twice. And then r is going to be 5. The cube root of 125. Is that giving us a minimum surface area? Well, here's my half of my number line. I'm looking at surface area derivative as a function of r, starting at 0. And the radius here could actually be infinite. So it is interesting to think about for this shape, right? If it has to hold a specific volume, you can't have a radius that's 0. You can have a radius that's slightly bigger than 0. And you could have, so you could have a super tiny, super tall can, that would be dumb. Or you could have a super wide, super flat can, which to me feels like a pancake, which would hold that much volume. But the point I'm trying to make is that the radius is between 0 and infinity. You could have the biggest can with the tiniest height, and it would hold all the volume if you made it wide enough. So our radius is between 0 and infinity, and my critical value is 5. Now this is where maybe I should have factored. Not really. But you could make an argument, well, if you'd factored, James, figuring out where it's positive and where it's negative would have been easier. Well, fine. I don't care. Here's my derivative, not factored. And I'm just going to figure out if it's positive or it's negative in each of these terms. So plug in the easiest number you can think of between 0 and 5, 1. 4 pi minus 500 pi over 1. That's going to be negative. 4 pi minus 500 pi, definitely negative. And then over here, pick a number that's easy to plug in, like 100, or even 10. 10's easy. Plug in 10, you get 40 pi. Plug in 10, 500 divided by 100 is 5. Or you can plug in like 1,000, right? 4,000 pi minus something over 1,000 squared is going to be super small. So this is relatively big number minus relatively small number is positive. Here's what you really could do. Say, hey, I know they asked me to find the dimensions that minimize the material, the amount of material, the surface area. So I know it's supposed to be a minimum. So you'd be like, hey, there's my critical value. And yeah, I'm totally checking that it's going to be, let's say I want it to be a minimum. So it's negative here and positive here. Definitely, I checked. It works. So typically you get what you want. If they ask you to find the thing that minimizes it, it's going to be a minimum. But some people, depending on the atmosphere, can be sticklers for checking this piece of information that it is actually a minimum. We're not done. We're almost done. They asked us to find the dimensions, plural. We found that the radius was 5 inches. We need to go back and find the height. Let's see if there's an equation for height. So the height is going to be 250 divided by 5 squared, which is 250 over 25, which is 10 inches. So that's our answer. A cylinder with a radius of 5 inches and a height of 10 inches minimizes the amount of surface area for that amount of volume. And the interesting thing is if you go to the store and you look at, like, especially the big cans of beans, you will notice that the diameter, which is twice the radius, is pretty close to the height. It's really like a true thing. We are actually trying to use math to optimize the amount of stuff we're using, right? We don't want to use more material than we have to. That's expensive. So yeah, you will see cans in the store. Now, not the smaller ones. Like the smaller ones, I think there's also shipping things to consider. The smaller cans are usually a bit taller than they are wide. But like the big cans of beans, especially, they're pretty much as wide as they are high, and they're definitely cylinders. So yeah, it's kind of neat. Math actually works for real things in real life.